Hello, everyone. In this presentation, our group will present a recent deep reinforcement learning paper titled CALM, Knowledgeable Agent by Offline Reinforcement Learning from Large Language Model Rollouts, published at New IPS 2024. This paper explores how large language models and reinforcement learning can be combined to create more knowledgeable agents that can solve tasks beyond what they have seen during training. We will discuss the motivation, methodology, experiments, results, and our critical evaluation of the paper. Reinforcement learning has achieved remarkable success in many areas such as robotics, games, and decision-making systems. However, reinforcement learning agents are usually limited by the data they are trained on. For example, if an agent learns how to move an object to the left, it may struggle when asked to move it to the right, even though the two tasks are very similar. The authors point out that real reinforcement learning agents often fail to generalize beyond the experiences contained in the training data. At the same time, large language models such as ChatGPT and Llama contain a huge amount of world knowledge learned from large text corpora. This raises an interesting question. Can we transfer the knowledge stored inside LLMs to RL agents so they can perform tasks they have never seen before? Previous research has already combined LLMs and reinforcement learning in different ways. For example, LLMs have been used for planning tasks, generating rewards, and high-level decision-making. However, most existing methods operate at the text level and do not directly help with low-level control. The main challenge is that LLMs work with text, while reinforcement learning environments use numerical state and action vectors. This creates what the authors call a semantic gap between the language and environmental data. To solve this problem, the authors propose CALM, a framework that extracts knowledge from LLMs in the form of generated rollouts and uses offline reinforcement learning to learn new skills. I will now hand over to Teng Wei Long, who will explain the background and research gap in more detail.
Thank you, Pradipa. Now I will go through the background and the critical research gap that the KALM framework addressed. To understand the core motivation behind this research, it is essential to first review two frameworks separated by a fundamental semantic gap. First, we have offline reinforcement learning. Offline reinforcement learning is highly useful because it allows agents to learn from static, pre-collected dataset without needing a real-time environment interaction. However, it has a massive bottleneck. Its success is strictly limited by the diversity of that training data. If an agent encounters a new situation that is not covered in its dataset, it lacks the ability to generalize and will typically fail. To solve this generalization problem, researchers look for a second tool, large language model. It is autoregressive models trained on the massive text corpora that embed comprehensive knowledge and reasoning capabilities. The advantage of large language model is it capable of understanding complex instruction and generating logical steps for tasks. While they excel at text-based reasoning, they are not designed to process the continuous numerical data found in physical environment. This brings us to the core problem identified in this paper, the semantic gap. There's a fundamental mismatch between these two domains. Large language model operates strictly in high-level text token, while physical environment operate on low-level continuous numerical vectors like specific coordinates or robotic joint angles. Therefore, raw textual output cannot be directly applied as the low-level execution signal required by robotic actuators. Prior research to integrate large language model and reinforcement learning fails because they only use the large language model for high-level text-based planning, like generating a command to go to kitchen. They completely fail to address the low-level control of how to physically execute that movement using precise numerical inputs and outputs. Therefore, a KALM framework was designed to overcome this semantic gap and achieve low-level continuous control using large language model knowledge. I will now hand over to Lam Tian Pang to explain the overall methodology of how they did this.
For the methodology of this research study, the proposed KLAM framework follows several procedural steps that enables the offline reinforcement learning agent to learn new skills apart from existing experiences in a given dataset, so it can perform and generalize to unseen tasks better. The figure here displays the detailed KALM framework that was used by the researchers of this study throughout the whole research. The procedure starts by collecting offline element dataset first, which is used to train a LLM model. This allows the LLM model to understand the meaning of states, actions, and environmental changes after each taken action, which builds the environmental understanding for generating rollouts in the next step. The second step involves imaginary rollout generation from the LLM model. The trained model is given new unseen goals and asked to generate imaginary rollouts, which are new sequences of actions, states, and observations that could achieve those goals. These roll-outs include novel skills not found in the original dataset and are thus combined with the existing training data. For the last step, new skill acquisition is achieved by training the reinforcement learning agent on both real interaction data and generated rollouts. This enables the agent to generate new action capabilities known as skills, thus learning a wider range of behaviors and improving its ability to handle unseen goals. Periophistic robustness and novel task generalization are used to evaluate the effectiveness of KLAM, which they evaluate whether the agent can recognize the same task expressed in different words, but also able to perform completely new tasks with different behaviors that were assigned in the training data. Overall, the key idea of KLAM is to use a large language model to imagine useful experiences for unseen goals, and then use those experiences to improve policy learning and generalization, which is the main significance of this research.
This is Fauzia. Now I'm going to talk about the technical details. At first, we have grounding the LLM. Here, our main target is to convert the states, the RL states and actions into a format which the LLM can understand. Usually, the LLMs can only understand text, but by introducing 4 modules, we convert it to an understandable format for the LLM. At first, we use the state encoder where we embed the states. Then we use the action encoder and we embed the actions. And then lastly, we have the state encoder and state decoder and action decoder where the embedding is reversed. Then we use 3 supervised learning tasks to further ground the LLM. We see that the agent learns the environment transition by seeing the present or current state and action, and then it predicts the new state, and this is the dynamics prediction. Then we have the rollout explanation where the trajectories are totally converted into textual description so that the LLM can understand what is happening. And lastly, the novel task or skill is acquired by the agent by generating new trajectories from a new goal description. Lastly, we integrate the offline reinforcement learning. Here, we choose 2 datasets. The first one is real dataset, and the second one is LLM generated rollouts. So we combine these datasets and name it as combined dataset. The offline RL trains the policy using both datasets. What is the benefit of offline RL? The first benefit is it is more diverse and it can acquire the novel skill and it can better generalize the unseen goals. And lastly, we don't need any extra environment to train this. Thank you.
Next, I will explain the experimental setup. KLM was evaluated into robotic environment. Clear robot, where a robot moves carable to target position, and MetaWalk, where a Soya robot performs tasks like pushing object, opening door, and pressing button. The research used 100,000 rollout goal pair for training and fine-tune the language model to understand that action and goal. KLM also immediately roll out, which provide extra training experience for unseen tests. The backbone model used was Llama 27B. The results show the KLM significantly improved performance compared to standard offline reinforcement learning vendors. For example, in clear robot novel test TQL with KLM achieved a 27.1% success rate compared to 15.5% for CQL alone. The improvement showed that imaginary rollout help robot learn new tasks and generally better to unseen situations. In summary, KLM illustrates adaptability, improve test performance, and demonstrates the benefit of integrating large language model with offline reinforcement learning. Thanks.
Hello everyone, my name is Lee and I'll be doing the analysis for my part. Now the core problem is that the reinforcement learning is heavily constrained by its training data set, and the solution to this is instead of using LLM directly as a policy or a high-level planner, Calm fine-tunes a pre-trained LLM to act as an imagination machine engine that bridges this gap. Now, the mechanism for this is that the grounding modifies the input-output layers of the LLM with multi-layer perceptrons to translate back and forth between textual goals and continuous numerical states and actions via supervised fine-tuning. Route generation prompts the grounded LLM to generate imaginary route simulated state action sequences for completely novel tasks, and skill activation combines this imaginary route with real offline data to train a standard offline RL policy, expanding the agent's capability beyond the original dataset. Now, the critique for this is that the strength is that it has innovative strategy. It smartly bypasses the latency and tokenization issues of using LLM directly for low-level continuous control by moving the LLM compute to the offline dataset generation phase. It has strong linguistic generalization. It successfully handles diverse linguistic phrasing and naturally incorporates complex world knowledge into robot trajectories. Now, the weaknesses of this is the state versus action disconnect. The appendix testing reveals that the fine-tuned LLM is noticeably better at imagining future states than accurately predicting precise low-level actions. There is a complexity ceiling limit. The performance breaks down on highly complex actions, and there's also severe physical hallucinations where joints are bent incorrectly and objects are not correctly placed. Now, the conclusion we can have is that Calm successfully demonstrates that the implicit word knowledge embedded within LLMs can be successfully translated into numerical, low-level physical robots to train robust RL agents. That'll be all from me. Thank you.